Welcome back. Today we are going to discuss about strengthening mechanisms of metals. So previous lectures we understood to move the dislocation which causes the deformation. So if by some mechanism we can make the dislocation difficult, we can increase the strength of the material. So which means that by doing something in the material we can increase the strength of the material. So metallurgical and material engineers are often called to design alloys having high strength. So the strength of the material must be increased. So that is the demand. So all strengthening techniques rely on this simple principle. Restricting or hindering dislocation motion renders a material harder and stronger. So the aim is to provide a restriction to the dislocation motion. So then dislocation will be reduced and more stress will be required for dislocation. So let us see the different strengthening mechanisms that are there for single phase metals. First one is by grain size reduction, solid solution alloying, and strain hardening. So deformation and strengthening of multi-phase alloys are more complicated. So it is a bit complicated in the case of multi-phase alloys. So first, let's see by strengthening by grain size reduction. Basically, grain boundaries will be restricting the dislocation motion. The size of grains or average grain diameter in a polycrystalline metal influences the mechanical properties. So in this figure, when a slip or dislocation takes place across this boundary, plastic deformation will happen. So during plastic deformation, slip or dislocation motion must take place across the common boundary, say from grain A to grain B. So in this figure, when during a plastic deformation, so dislocation motion will be taking place from this grain A to grain B across this common boundary. So this grain boundary, it will act as a barrier to dislocation motion for two reasons. The first reason is since two grains are of different orientation, a dislocation passing through into grain B will have to change its direction of motion. So the direction of motion of grains will be changed. So next is the atomic disorder within a grain boundary region will result in a discontinuity of slip planes from one grain into another. So the slip planes will be discontinued due to the movement of atoms. So these are the two reasons for which the grain boundary acts as a barrier to dislocation motion. So when a fine grain microstructure machined by a coarse grained annealing, we will get a coarse grained microstructure. So as you can see here in this microscopic image, there will be grain boundaries after very small distances. In this case of a fine grain microstructure, there will be grain boundaries after very small distances. So that here we will require a large amount of stress for dislocation moment. But in the case of a coarse grain microstructure, the dislocation moment will be easier due to its larger grain size. So thereby decreasing the grain size, we can increase the strength of the material. that is written here. A fine grained material, that is one has a small grains, is harder and stronger than one that is coarse grained. Since the former has a greater total grain boundary area to impede the dislocation motion. So this fine grained microstructure has a greater total grain boundary area to restrict the dislocation motion. So here we can see a relation for grain size reduction. So the grain size reduction leads to the increase in strength, and that is given by a Hall-Petch equation. So the yield strength sigma y varies with grain size according to. So we can say this sigma y is the final strength. Sigma y is equal to the final strength sigma y is equal to the initial shear strength sigma 0 plus a constant k times inverse of the square root of average grain diameter, that is d raised to minus 1 by 2. So the final strength will be equal to initial strength plus a constant k into the square root of inverse of the average grain diameter, that is d. So this expression termed as Hall-Petch equation. So here d is the average grain diameter and sigma 0 and ky are the constants for a particular material. So it should be noted that the Hall-Petch equation is not valid for both very large grain and extremely fine grain polycrystalline material. So it is not valid for very fine and very coarse polycrystalline materials. So grain size may be regulated by the rate of solidification from the liquid phase and also by plastic deformation followed by an appropriate heat treatment. So it should be mentioned that the grain size reduction improves not only the strength but also the toughness of many alloys. So as we can say that this is the only method which increases both the strength and toughness of the material. But the problem is by using this method, this is the most preferred method, but this method we can only increase the strength to up to a particular level. So to increase the strength above that level, we have to go for other methods. So next method is solid solution strengthening. So it is a second method to increase the strength in solid solution, increase the strength in material. So is there another technique to strengthen and harden metals is alloying with impurity atoms that go either in substitutional or interstitial solid solution. So here what we are doing is the metals are alloyed with impurity atoms. So an alloying with the impurity atoms is happening here. So high purity metals are almost always softer and weaker than alloys composed of same base metals. So increasing the concentration of the impurity results in attendant increase in tensile and yield strength. So by increasing the concentration of the impurity on a high pure metal, the strength and the yield strength will increase. We all know this method. So impurity atoms that go in the solid solution impose lattice strains on the surrounding host atoms. So in the surrounding host atoms, a lattice strains are developed. So here the compressive and the tensile region matches and the dislocations will be restricted. So lattice strain field interactions between dislocations and impurity atoms results in restriction of dislocation movement. So this is one of the most powerful reasons to make alloys which have high strength than pure metals. So the interactions between the dislocations and impurity will result in a restriction of the dislocation movement. So here we can see the different types of solid solutions. There are two types, that is substitutional solid solution and an interstitial solid solution. So in substitutional solid solution, the solute and the solvent atoms will be roughly of the same size, and the solute atoms will replace the solvent atoms in its position in the crystal structure. But in the case of an interstitial solid solution, the solutes will be much smaller than the solvent atoms, and they will occupy the solute atoms will occupy the interstitial positions in the lattice site. So these are the two examples we can see of the substitutional solid solution and the interstitial solid solution. So this is here we can see representation of a tensile strain and compressive strain. So in tensile here we can see the tensile lattice strains are imposed on host atoms by a smaller substitutional impurity atom. So here a tensile lattice strains are imposed, and which cause the possible locations of smaller impurities as here. So related to the edge dislocation, there is a partial cancellation of impurity dislocation lattice strains. And as a result, the impurity atoms will be possibly occupying this particular region. But when the compressive strains are imposed on the host atoms by a larger substitutional impurity atoms, the possible dislocations will be here. Okay, so next we can see the size and effect of strain field shape. So the shape of strain fields caused by defects and those around the dislocations have a significant impact on strength of solid. So the shape of strain fields will have an impact on the strength of the solid. But in substitutional solids generally stretch the lattice uniformly, producing hydrostatic strain fields around the solutes. So a big substitutional solute, it will keep on stretching uniformly in spherical manner, and the strain fields around the solutes will be produced. If these hydrostatic strain fields are relatively weak, and the obstacles to further dislocation motion in comparison to shear strain fields. So that is, these hydrostatic strain fields, they will be weak obstacles for further dislocation motion. So here we can see an interstitial solution and a big substitutional material and a small substitutional material. So we can compare how is solid solution strengthening happening with the material. For example, if you take a 24 karat gold, and that gold will be too soft, and if we and it will not have much strength, and it will be easily deformed. So if we put in 16% of silver and a 9% of copper, so we will be obtaining an alloy that will exactly like the pure gold, but the strength of that alloy will be higher and the durability will also be higher. So in a 14 karat gold, there is only a 58.3% of gold, and the rest are copper and silver. in an 18 karat gold, when we alloy with 16% silver and 9% copper, we will get an 18 karat gold, and which will be having a 75% gold. So this is the difference between a 14 karat, 18 karat and a 24 karat gold. These three are 14 karat and 18 karat and a 24 karat gold, and it's difference between a pure gold. So the resistance to slip is greater when impurity atoms are present, because the overall lattice strain must increase if a dislocation is torn away from them. So the resistance to slip increases with the addition of the impurity atoms, and if the dislocation is torn away from them, the lattice strain must increase. So why a solid solution strengthening works? So this is a vector. You can see the arrangement of atoms. The small atoms likes to be here. So small atoms are likely to be present over here, as they reduce the lattice strain caused by the dislocation. But the big atoms or the interstitials we have seen will be living here, as there is more space. So the atoms will diffuse into dislocations during high temperature, and which then exerts forces on dislocations to pin them together or to restrict motion. Okay, from this figure you can see the difference between edge dislocation and a screw dislocation. In edge dislocation, we will be having both dilational and shear strain fields. That is, we have distortional strain fields in edge dislocation. But in the case of screw dislocations, there will only be shear strain fields. So here we can see both shear strain field and dilational strain fields. But in screw dislocation, we can see only the shear strain fields. So here you can see a small solute aggregates to compressive region over here, and a large solute aggregates to tensile region in here, and here there will be a tension, and here there will be a shear, and here there will be a compression. So these are the regions of compression, shear and tension. So here we can see an example of a nickel content with its variation. So this is the percentage of the nickel content in the x-axis. In the y-axis we can see tensile strength, yield strength and elongation. You can see here, as the percentage of the nickel content in a copper nickel system, or percentage of the nickel content when it increases in a copper nickel alloy, as the percentage of nickel increases, the tensile strength you can see will also increase, and also the yield strength will also increase here. But here we can see the ductility or the percentage of elongation, it will be decreased or will be reduced. So usually this is the case of the most of the strengthening mechanisms, as the when alloying with the we can say in this case of the copper nickel alloy, when the percentage of the nickel increases, the yield strength and the tensile strength keeps on increasing, but the percentage of elongation or the ductility of the material will be reduced or will be decreased. So that's about a solid solution strengthening. So next we can see strain hardening. So strain hardening is also known as work hardening or a cold working. So strain hardening is the phenomenon whereby a ductile material becomes harder and stronger as it is plastically deformed. So strength of the material is increased with the loosened ductility. Sometimes it is also called as work hardening, as I said, or because the temperature at which the deformation takes place is cold relative to the absolute melting temperature of the metal, it is also called cold working. So it is also called as a cold working or a work hardening. So most metals strain harden at a room temperature. So strain hardening takes place in most metals at the room temperature. So the dislocation density in a metal increases with the deformation of cold work. So this increase leads to dislocation interaction. So with the deformation or the cold work, the dislocation density increases, and this increase in dislocation density will lead to the dislocation interaction. So the dislocation strain interactions are repulsive, and the net result is that the motion of a dislocation is hindered by the presence of other dislocations. So the more dislocation interactions, more will be pinning down of the dislocation, and more will be the energy or the stress required. And this dislocations of same signs, they will repel each other. So that is what the dislocation strains interactions are repulsive. If the dislocations are of same sign, they will repel each other. So as the dislocation density increases, the resistance to dislocation motion by other dislocation becomes more pronounced. So the resistance will be increased. So the resistance to dislocation motion will be increased with the increase in the dislocation density. Thus, the imposed stress necessary to deform a metal increases with increasing cold work. So the stress to deform the metal will be higher. As a result, the stress required to deform the material will be higher. So here we can see it is sometimes convenient to express the degree of plastic deformation as percent cold work rather than as strain. So the degree of plastic deformation is expressed here with the percentage of cold work done. So the percentage of cold work is defined as here like this. The percentage cold work is equal to A0 minus AD by A0 into 100. So here A0 is the original area of the cross section that experiences deformation, and AD is the area after deformation. So A0 is the area before deformation and AD is the area after deformation. So let us see the mechanism of strength hardening. So the dislocation density in metal increases with the deformation or cold work due to dislocation multiplication or the formation of new dislocations. As we seen earlier, so the dislocation of metal increases, deformation or cold work due to dislocation multiplication or the formation of new dislocations. So with the deformation, the dislocation density increases. So consequently, the average distance of separation between dislocation will be less, or the separation between the dislocation decreases, and such that these dislocations will be positioned closer together. On the average, dislocation strain interactions are repulsive. So as we have said earlier, these dislocation strain directions of the same sign, they are repulsive, and the net result is that the motion of dislocation is hindered by the presence of other dislocations. So this in exam point of view, you can write as a mechanism for strain hardening by writing one by one. You can explain. So first, due to dislocation motion, the dislocation density, dislocation multiplication, the dislocation density increases, and the average distance of separation between the dislocations decreases, and the dislocation strain interactions are repulsive, so that the net result will be the motion of dislocation or the motion of dislocation will be restricted or pinned down, and as a result we require a large amount of stress for the dislocation to be generated. So here we can see an example of a 1040 steel, brass and copper. So due to strain hardening, in the x-axis we can see the percentage cold work, and in the y-axis there is yield strength, tensile strength and ductility. So due to strain hardening, when the percentage of cold work increases, the yield strength and the tensile strength it keeps on increasing. You can see for in the case of copper, brass and steel, the yield strength increases, as well as the tensile strength also keeps on increasing. But here you will lose the ductility. So the ductility of the copper, brass and steel will be decreased or reduced as the percentage of cold work increases. So as the percentage of cold work increases, the ductility or the percentage of elongation will be decreased. So that's all about strain hardening. In the next class we will be discussing what is annealing and what are the different stages in annealing. So thank you.